So in the last video we have seen what are known as shortest paths problem. In this class we are going to focus on what's known as minimum or maximum spanning trees. The shortest path problems were defined both on directed as well as undirected graphs, but the minimum spanning tree or the maximum spanning tree problem is defined only on undirected graphs. Let's look at so what this problem is in this video. Before we talk about the spanning trees, let's quickly define some definitions which are required. We recall that when we talk about the spanning trees, we will only be concerned with undirected graphs. If you are talking about shortest paths are defined both in directed as well as undirected graphs. But the spanning trees are discussed only in the context of undirected graphs. For this entire video, we are going to assume that the given graph is an undirected graph. So in an undirected graph, we say that two nodes are connected if there is a path between them. So you should be able to start at one node, follow a path and reach the other node. If that happens, then we say that these two nodes are connected. An undirected graph is said to be connected if there is a path between every pair of nodes in the graph. Two nodes are said to be connected if there is a path between them. A undirected graph is said to be connected if there is a path between every pair of nodes in the graph. Let's look at this example. So this is a connected graph because if you take any two vertices, there is a path connecting them. For example, if you take 0 and 3, from 0 I can go to 1 and from 1 I can go to 3. So there is a path from 0 to 3. Similarly, you can construct paths from any two pair of nodes in this graph. So this graph is a connected graph. So whereas this graph that you have is not a connected graph because there is no path from 3 to 5. Starting with 3, there is no way to reach 5. Similarly, starting with 6, you cannot reach 7. So this is not a connected graph. So when the graph is not connected, then we talk about what is known as a connected component of a graph. Which is a maximal connected subgraph of G. So what is the subgraph of G? G has set of vertices and set of edges. If you take another graph where the set of nodes is a subset of the original graph and the set of edges are also subset of the edges of the original graph, but the endpoints of these edges that you pick in the subgraph should be the nodes of the subgraph that you have picked, right? So if that happens, then that's called a subgraph. So the connected component is a maximal connected subgraph of G. For example, you can start with 0. So when you start with 0, so you mark all the nodes in a set which are all reachable from 0. So if you start putting all the vertices which are reachable from 0, you get the set 0, 1, 2, 3 and 4. So this is called a connected component because if you take any two vertices in this connected component, they are reachable from each other. After you do this, then you pick another vertex which is not connected to 0. Then you repeat the same thing. Collect all the vertices which are connected to 5. So that becomes another connected component. And so if you are still left with some more vertices which are still not collected, you start with that and build the connected component there. So the connected component is a maximal connected subgraph of G. So you can imagine that the set of nodes is a disjoint union of set of nodes in the connected components. For example, in this graph you can clearly see 3 connected components. So one is the first connected component which has 0, 1, 2, 3 and 4, and the second one which has 5 and 6, and the last connected component that you have is 7. So the important thing is that the entire set V can be written as disjoint union of V1, V2, Vk, where k is the number of connected components that the given graph has. The important property of these connected components is that if you take any two vertices within the same connected component, they are connected in the sense that if you take any two vertices in the same connected component, there is a path connecting them, path between them. But if you take two vertices in the different connected components, the very basic fact that they are in the two different connected components, in the graph there will be no path connecting these two vertices. So you are going to given a graph which is not connected, so you are going to break down into different connected components with the property that if you take any two vertices in the same connected component, there is a path between them, and if you take two vertices in the two different connected components, there will be no path between them. So we will use these facts sometimes later during the course. So as of now, so you know what is a when you say two vertices are connected, what's a connected graph, and what's the connected components of a graph. If the graph is already connected, then the number of connected components in the graph is going to be exactly 1, right? So every vertex is reachable from each other, so you can't break this into different connected components. Yeah, undirected graph is said to be a tree if it is connected and does not contain a cycle. So you know what's a cycle? So this first graph has several cycles. You can start with 1, you can go to 2, then you can come back to 4, and again go back to 1. So the cycle is a path where the starting vertex is same as the ending vertex. So 1, 2, 4, 1 is a cycle here. This is not a tree. A graph is called as a tree, yeah, if it satisfies two conditions. One condition is that it should be connected and it should not contain a cycle. If you just take the node with 5 and 6, the subgraph 5 and 6, if you just consider that as a graph, that's a tree, because 5 and 6 are connected and there is no cycle there. Similarly, if you just consider this one vertex which is 7, that as a graph, then by default this is connected and there is no cycle there. But if you take the entire graph here, this is not connected and there are cycles, so this is not a graph. So the forests are the ones which do not contain a cycle, right? So if you consider the vertex graph of 5, 6 and 7, this is not a tree because 5 and 7 is not connected. It's not a connected graph. There are two connected components, but it doesn't contain a cycle. So the forest is a collection of trees. Forest will not contain cycle, but the forest need not be connected. Okay. So repeat, a undirected graph is said to be a tree if it is connected and does not contain a cycle. A forest is a collection of trees, which essentially means that the graph need not be connected, but it doesn't contain cycles. The binary trees that we have seen so far in the course is a special kind of trees. The trees are special kind of graphs, right? So the binary trees are special kind of trees, and trees are special kind of graphs. So you can imagine that the binary search trees that we have seen are special kind of graphs. Okay. So the set of nodes in the binary tree is exactly equal to the set of nodes in the graph that we have, but you have to define what are the edge sets in the graph. The edge set is basically you just look at every node and its parent, right? So we need to so what's an edge? Edge is you have to give two endpoints of the nodes. One node is the node itself, and you take the parent of the node. If you look at the collection of all order pairs like x comma x parent, that becomes an edge in the graph. Okay. So the summary is that so the graph are more generalized generalization of trees, and trees are more generalization of the binary trees that we have seen. So binary trees that we have seen is a very specific kind of tree, which is a very specific kind of a graph. So we will look at an important theorem called the theorem says the following: G is an undirected graph with n nodes, and any two of the following should imply the third one. The first condition is that it is connected. G does not contain a cycle, and G has n minus 1 edges. If you give me a graph which satisfies any two of these, so what this theorem says is that the third one should be obviously true. So if this theorem is true, what it implies is that every tree will contain exactly n minus 1 edges, because according to the definition of tree, it's connected and does not contain a cycle. So that means that the condition 1 and 2 is satisfied. So the third condition should be true. So one of the corollary of this theorem, if this theorem is true, is that a tree will have exactly n minus 1 edges. So how do you prove such a theorem? So what this theorem is saying, if you assume any two conditions, the third condition should be true. So there is the one way you have to prove this is that you assume 1 and 2, and 1 and 2 implies 3. Assume 2 and 3 and prove 1, and assume 1 and 3 and prove 2. Right? So that's precisely what we are going to do. So before we get into the proof, let's make a small observation. Let's start with a graph G, So I will only pick the set of nodes in the graph, and I'm going to start adding one edge at a time, right, into this graph. Initially I have all isolated vertices. The number of connected components is exactly equal to n because nothing is connected to anything. Then I start adding one edge at a time, right? So you can consider the edges in any order that you wish. Okay, so now there are two things can happen. So when I start adding an edge, the edge can go across the connected component. If the edge that I'm going to add into the graph goes across the connected component, then the number of connected components decreases by 2. This, if we add an edge which goes across the connected components, these two connected components will be merged and you'll have one connected component instead of two. It's easy to see if you add an edge uv between where u and v belong to two different connected components. Let's say that u belongs to the first connected component and v belongs to the second connected component. After you add this edge, what we are saying is that all the vertices put together from the first connected component, second connected component will become a connected component. So why is that true? If you take any vertex in the first connected component, there is a path to v, and from v you can reach u, and from u, because u belong to another connected component, you can reach any other vertex in the second connected component. So if you take any vertex in the first connected component and any vertex in the second connected component, you can find a path through this edge u comma v in the graph. So if you end up adding an edge which goes across the connected components, you will end up merging the two connected components to which these two endpoints actually belongs to, and the impact of this is the number of connected components in the graph decreases by 1. So on the other way around, other thing can happen is that when you try to add an edge, you might end up adding an edge which is going within the same connected component. The moment you add an edge which goes inside the connected component, what you will end up doing is you will end up introducing a cycle. If u comma v is an edge which is going within the same connected component, because u and v belong to the same connected component, there should be a path from u to v, and you are adding an edge v comma u. So you can take the path from u to v, reach u, and then take this edge and come back to v. So you have created a cycle containing the edge u comma v, right? So what we have in summary is that we are doing the following experiment. We start with only the set of nodes, no edges, and try to add one edge at a time in any order. So what we have observed is that if you add an edge which goes across the connected component, the number of connected components will reduce by 1, and if you add an edge which is going within the same connected component, then you are introducing a cycle. So this is all what is required to prove this theorem. So what remains is just go through the proof of this theorem in 3 different cases. Let's look at the first part of the proof. So we'll assume that 1 and 2 are true and try to prove 3. So we will assume that the graph G is connected and G does not contain a cycle, and we'll try to prove that G will have exactly n minus 1 edges. Since G is connected, since G does not contain a cycle, after adding k edges, all the k edges should have gone across the connected component. So even if you had one edge which is going inside the connected component, we would have introduced a cycle. But since given that the condition 2 says that the graph does not contain a cycle, so if you add k edges, every time when you add this edge, it should go across the connected component, and every time when you add an edge which goes across the connected components, the number of connected components will reduce by 1. So if you end up adding k edges, the number of connected components after adding k edges will be exactly equal to n minus k. But the graph is connected, so that means that there is only one connected component if you end up adding all the edges. So the number of edges that you need to add in order to get one connected component from n number of connected components is exactly equal to 1. Because if you add k connected components, so the number of connected components is n minus k, and it's given that the graph has only one connected component, so n minus k has to be 1, implying that k is equal to n minus 1. That means that you have exactly n minus 1 edges, and each time when you added these edges, you did not create a cycle because all of them went across, and you reduce the number of connected components from n to exactly equal to 1. So this proves that 1 and 2 implies 3. Let's look at the proof for 2 implying 3. The ideas of the proof is exactly the same. So we'll again assume that G does not contain a cycle. So if you end up adding k edges, you will be left with n minus k connected component. You have given the fact that the graph has n minus 1 edges. So after you add n minus 1 edges, none of them introduce a cycle. So you have only one connected component. If you have only one connected component, that basically means that the given graph is connected. So now let's look at the proof for 1 and 3. So 1 says that G is connected and it has exactly n minus 1 edges. So we will do the same experiment. After you add k edges, you are left with n minus k connected components. But given that n minus 1 edges you are going to add, so if you add n minus 1 edges, and if finally you ended up getting up with exactly one connected component, that means that all the n minus 1 edges that you have added should go across the connected component. Even if one of them went inside the same connected component, you would not have been left with exactly one connected component. But it's given, we are assuming that 1 and 3, so there are n minus 1 edges, and eventually you have a connected component. So it should happen that all the edges that you have added must have gone across the connected component, which implies that the given graph did not have a cycle. So the what all that you need to remember to prove this theorem is simple. When you add an edge which goes across the connected component, the number of connected components reduced by 1, and if you try to add an edge which goes within the same connected component, it will introduce a cycle. With this, you can, it's just a matter of technically writing this proof, assuming two conditions and deriving at the third condition. So as I mentioned earlier, one of the corollary of this is that if you give me a tree, because of this theorem, so the tree is connected and does not contain a cycle, so every tree should have exactly n minus 1 edges. So now it's time to define what's a spanning tree. Spanning tree of a graph is a subgraph of G, which is a tree with n nodes. In other words, the nodes of a spanning tree will be same as the nodes of the graph, but it will have exactly n minus 1 edges. Since the tree it cannot contain a cycle, so since it is a tree which cannot contain a cycle and there are exactly n minus 1 edges, which means that the spanning tree should always be connected, right? That's the implication of the theorem. You're going to pick n minus 1 edges, and this is the tree. So since it's a tree, it should be connected and there should be no cycle, so that means that there will be exactly n minus 1 edges. So you can flip around and also always say that I pick n minus 1 edges so that the subgraph that I pick is going to be connected, which would imply that there will be no cycle there. Or if you pick n minus 1 edges and ensure that there are no cycles there, you still get a tree, right? So so what's the definition? You're going to get given a graph in the spanning tree, the set of vertices will be exactly the same, but you're going to pick n minus 1 edges so that they don't form a cycle. Or after adding this n minus 1 edges in the spanning tree, this subtree that you have is still going to be connected. Such a subgraph is called the spanning tree. So once you have what is a spanning tree, then we can define what is known as the weight of the spanning tree. See, if the graph is connected, then the weight of the spanning tree is defined as the sum of the weights of the edges in the spanning tree. You take the spanning tree is a collection of n minus 1 edges, you add up the sum of all these edges, so that becomes the weight of the spanning tree. So once you know what's the weight of the spanning tree, then you can define two problems. One is called as the minimum spanning tree, and the another one is the maximum spanning tree. So both we call it as MST. Minimum spanning tree is a spanning tree with the minimum weight. You consider all spanning trees and give me a spanning tree with the minimum weight. That is called as the minimum spanning tree. Maximum spanning tree is a spanning tree with maximum weight. So you given a graph, consider all spanning trees and compute the compute all the spanning trees and give me the spanning tree which has the maximum weight. Unlike the shortest path problems, so we said that in the case of shortest path problem is solvable in polynomial time, but the longest path problem is not solvable in polynomial time. But that's not the case, the story of the spanning trees. So both minimum spanning tree and the maximum spanning tree both are solvable in polynomial time. So more or less, so we'll see that if you study, for example, an algorithm to compute the minimum spanning tree, you can just tweak this and make some small modification to get the maximum spanning tree. In this course, we're going to study two efficient algorithms. One is known as Prim's algorithm and another one is Kruskal's algorithm. So both of them have the same complexity as the Dijkstra's algorithm, which is V plus E into log of E. So we'll come back to these two algorithms, study these two algorithms in detail. So probably we will not have time to look at the proof these algorithms, but we will understand what these algorithms, how to implement this, and what the complexity of this, and the proof why these algorithms actually computes the spanning minimum and maximum spanning trees correctly is deferred for some time. And so so that's what we're going to see in this course in the next couple of videos. So in this video we have seen so what are known as minimum spanning tree and maximum spanning tree problem on undirected graphs, and we said that both the problems are solvable in polynomial time, unlike the case of shortest path problems versus the longest path problem. So yeah, I think it's time to sit and think what is special about the spanning tree problem, so that you can solve min-max both versions. But in the case of shortest path problem, the min was solvable in polynomial time, but not the max. At the same time, we want to see whether the brute force algorithm will solve the minimum or maximum spanning tree problem. So what do you mean by the brute force? It's very tempting to look at given a graph. Let's consider all possible spanning trees. If you can consider all possible spanning trees, you can compute the weights of them and then keep track of the minimum and maximum. This is an algorithm which will always give you the minimum and maximum spanning tree. But if the number of spanning trees that are possible becomes exponential, then this brute force algorithm is not efficient or solvable in polynomial time. So if I take a graph which is a complete graph, which has n vertices in it, every node is connected to every other node. So we want to ask the question, how many spanning trees does it have? If it is exponential, then clearly the brute force algorithm to find the min and max spanning trees will not work. But if that is polynomial time, then we have a straight away polynomial time algorithm to compute the minimum and maximum spanning trees. So the question that we want to ask you is, given a complete graph with n number of nodes, how many spanning trees can it have? We'll find the answer to this question in the next video. Take a quick break and come back quickly.